Hey y'all, welcome back to another round of engineering. And yeah, let's keep going. The last topic that we have to discuss for the chapter is a topic of Thevenin and Norton equivalent circuits. Now, the idea here is that circuits can get rather complicated. They can get large, they can get arduous, and usually you have people from different teams working on different portions of the circuit. You can imagine something like a motherboard where one team might be working on the sound card, another team might be working on the processor unit, and another one with the PCIe lanes connecting the processor to various peripherals, if you will. And so the question then becomes, how do you approach working on an entire complicated circuit as individual teams? And how do you ensure that these pieces and parts can come together? Well, one of the interesting ideas that Thevenin, I believe he was French, came up with was an idea about linear circuits. So this is the one restriction that we have to think about, is that the circuit has to be linear. In other words, we can approach it using our matrix techniques. Okay? And he found out that if you have a linear circuit, and it doesn't matter how complicated it is, if you have a linear circuit, it can be approximated or modeled as a single potential supply called the Thevenin potential. So you can model it as a single potential supply and a single resistor. And this is generally referred to as the Thevenin resistance, RTH. So you have a huge complicated circuit, and I'll leave the open terminals here with a load across it. As long as your circuit is linear, you could take this huge rigmarole and approximate it as a single potential and a single resistor. Now, hopefully you can see the advantage of this. Imagine for a moment, and I won't draw out everything, but again, imagine that you have some complicated circuit where different pieces, piece 1 sends a signal over to piece 2, and piece 2 sends a signal over to something else on the board, say piece 3, and piece 4 over here. Piece 3 sends it to piece 4. Okay? No longer do you need to know the specific details of the preceding pieces in order to worry about or make sure that your piece works properly. Okay? What you need, say you're the team working on piece 2, all that you need to know is what is the Thevenin potential and the Thevenin resistance of this entire block. And with that, those two pieces of information, you can then go ahead and analyze your part of the circuit. Okay? So it's a way of, I call it black boxing. You can ignore the details of the circuit, you can black box it, and still appropriately model the reaction of your load, which is pretty cool. So that's what Thevenin found out. Norton, and I would have to go and look at the history of the development of these two ideas, okay, so I'm not as well familiar with it. Norton has a similar idea, but using current sources instead of potential sources. That hopefully doesn't strike you as being too terribly odd, because if you take the Thevenin potential and the Thevenin resistance and perform a source transformation, you know that you can create a current supply in parallel with a resistor, RTH. And then, of course, you can have your load resistance, R load, right here. The current supply has a value of the Thevenin potential over the Thevenin resistance. And this is sometimes called the Norton current. Okay? So Norton equivalent is simply the Thevenin the Thevenin circuit and then a source transformation. Hey, sometimes you just get to pick that low-hanging fruit. Lucky duck. So then the question is, how do we get the Thevenin potential, the Thevenin resistance? One way to go at it would be to simply do your source transformations until you collapse the entire circuit so that it contains only one potential supply, one resistor, and the load resistor. That's one way to do it. But there's other ways as well. So here's another way to do it. So the first piece is remove the load resistor from circuit. In other words, you're going to create a break between the two terminals where the load resistor is. Okay, so you remove that from the circuit altogether. And then two, calculate, I'll call it delta V, the potential drop across the load. Okay. Sometimes you will see this referred to as the open circuit potential. Okay. So the potential drop between the two nodes where the load is going to be attached. That is going to be your Thevenin voltage. Now, we also need the resistance. And of course, excuse me, I should go back. You can see where all of your previous analysis techniques would help you with this piece. Okay? So again, whatever suits your fancy, superposition, node voltage, mesh current, KVL, KCL, take your pick. Okay. To get your Thevenin resistance, okay, so to get RTH, you have to deactivate the sources. So deactivate, that's the idea that we introduced when we said superposition. Okay, so RTH, what you need to do is deactivate independent sources, okay, and calculate REQ. And I'll put in here all independent sources. And then if you deactivate your independent sources, you calculate the equivalent resistance, and I'll put as seen from terminal. So that place where you removed the load resistor, those are the two terminals, you deactivate all of the other sources in the circuit. So anywhere where you have a current supply, an independent current supply, put a break. Any place where you see a potential supply, an independent potential supply, put a wire. Okay. Then, starting from one terminal, calculate the equivalent resistance to get to the other terminal. That equivalent resistance will be your Thevenin resistance. You should also note, okay, that right here, this step 3, doesn't work if you have dependent supplies. Notice I said independent sources. So this will not work if you have dependent supplies. So maybe I should call this 3A. Okay? Now you say, well, what do I do? 3A doesn't always work. Right? Is there another way to do it? Yes, of course. Yes, there is. So I'll call this one 3B. 3B. Or now 3B, 4. Okay. We'll have to figure it out. Okay. So another way to get the Thevenin resistance, okay, is to think and use Ohm's law. So we already have the potential drop across the terminals. The other thing that we will need is what is called the short-circuited current. And how does that work? Rather than deactivating the sources and figuring out the resistance directly, what we are going to do is leave the sources in the circuit, and rather than having the load resistor, we're going to put in a wire. Now, what do we want to do? We want to find the current which will flow through that wire that we have introduced into the circuit. That current is called the short circuit current. I'll probably label it as I short circuit, ISC. Okay. So place wire at terminals and find current through. Your Thevenin resistance, you can probably guess what it's going to be, is going to be your open circuit, maybe I'll call it open circuit potential, divided by your short circuit current. So that's a way of getting it, if you will, indirectly. Find the open circuit potential, find the short circuit current, and take the ratio of the two. That will also give you the Thevenin resistance. So those are two different ways of doing it. I'll say directly 3A or indirectly 3B. I will say they should both lead to the same answer. One of these tends to be faster in terms of experimental procedures. It would be the second one. Okay? All you do, take your DMM, put it at the two terminals, boom, you've got your voltage. Unplug the wire, put it in so you can make a current measurement. Plug it back into your thing. Boom, you've got your short circuit current. So the second method tends to be faster from an experimental standpoint. From calculating theoretically, it's a mixed bag. It depends on what the circuit looks like. But from an experimental point of view, the second one's probably the faster of the two. Just be aware. Well, let's get a flavor. Let's go ahead and get an idea about how to do this on a circuit. So we'll go back to our normal circuit here, our example circuit, and let's go ahead. We'll consider the 8 ohm resistor to be the load. And what we would like to do is find, so we'll do 2 steps here. Let's find VTH and RTH. And let's do it using both of the methods by deactivating the source and finding the equivalent resistance, and by short-circuiting the terminals and finding the short-circuit current. We want to make sure that those two match up at the end of the day. Okay? And then we can use those to find the current through the 8 ohm resistor. So find VTH, RTH, and I'll put and the short-circuit current. Find all 3 of those. And then we'll use those respective things to get the current flowing through the 8 ohm resistor. Okay. Well, let's go ahead. The first step is to find VTH. In other words, let's pretend for a moment that this 8 ohm resistor is not here and it is a break. So the circuit that I am left with looks something like this. And we're done, right? There's a break, so we don't have to worry about that lower connection. So what's VTH? I assume you have it. Let's see here. For lack of a better, let's go ahead and do mesh current. So I'll just take it going clockwise. And I have something that says, okay, well, a jump of 10 volts minus the 5 volts. minus 3I minus I equals 0. And so I get in this situation that my mesh current 4I, oops, excuse me, I forgot my I, get that my mesh current is negative 4I equals negative 5. And so my mesh current is 5/4 of an amp. Okay. And there's my two terminals. Well, if the current is 5/4 of an amp, then I should be able to figure out what the potential difference is between my high and low sides of the terminal. Okay. I could either do 10 volts minus 5/4. That's probably easier looking at this top line. So what I get is that VTH is equal to 10 minus 5/4 of an amp times 1. And so overall, I get that it's 8.75 volts. Well, now let's go ahead and get the second piece of information. Let's go ahead and calculate what our Thevenin is, and we'll do it directly. So we're going to leave our two open terminals, and we need to deactivate our potential supplies. To deactivate a potential supply, that is like treating it as if it were a wire. So we'll leave the wire. We've got a 1 ohm resistor, wire, and a 3 ohm resistor. And then back to the terminal. So if I want the equivalent resistance or the Thevenin resistance for this situation, okay, we see that, okay, we've got our two resistors in parallel. Okay. So what is this? This is 3/3. Okay, so we get, I don't know why I put a 1/2 there, excuse me. We get 4/3 to the -1, so we get 3/4, 3/4 of an ohm. And so it turns out that in this situation, that is the Thevenin resistance, RTH equals 3/4 of an ohm. Okay. So what does this mean? And we'll go back to the short circuit current in a moment. What does this mean? I can take this circuit and I can reduce it down to my load resistor, 8 ohms, in series, I had to think about that, with a potential source of 8.75 volts and a resistor of 3/4 of an ohm. From the perspective of the load resistor, these two circuits that I have drawn are completely equivalent. There is no way for the 8 ohm resistor to distinguish between those two circuits from an electric point of view. It gets the same potential, it gets the same current. Those two circuits are equivalent. Pretty cool, huh? And for a cherry on top, we could always find the current flowing through the 8 ohm resistor. In fact, sure, why don't we do it? The current flowing through, you can see, is the voltage divided by the total resistance. So we have 3/4, we have 8. So if I divide that, or if I find a common term, 32/4 plus 3/4, so I get 35/4. That's the current. And of course, the eagle eyes among you realize that that's just 1 amp, which we knew from our previous things. So fortunately for us, all of the stuff fits nicely together. Cool, huh? Well, let's take a step back. Okay. Let's go ahead and see if we could do the short circuit instead. Okay. So, what do we have there? Well, I'll go ahead and get rid of this. So can we get the short circuit and get the Thevenin resistance the other way? Hopefully I won't regret erasing all of this later. Okay, there we go. So can we get the short circuit instead? Sure. So rather than deactivating the sources and finding the equivalent resistance, we could leave those sources in there. V plus minus, we have our 10V, our 1 ohm. And now, rather than having a break, we're going to run a wire. There we go. So let's see here. How do we want to analyze this? Sure, I'll just go for mesh current again. So I'll go 2 clockwise ones here. And what do we get at the end of the day? Well, for the top loop, I should give you a second. Go. Okay. So for the top loop, what do I get? I get a, let's see, a minus 5 volt drop, minus 3, I'll call it I top, minus I bottom. So I'll use top and bottom here. And then I have a minus 1 top. And then I have a plus 10 equals 0. There we go for the first one. For the bottom one, what do we have? We have, okay, a drop, so minus 3. We have I bottom minus I top. And then we have a plus 5 jump equals 0. Okay. Well, let's go ahead. So what I have at the end of the day, so if we plug these into our matrix and do our algebra, what I have at the end of the day is that the top current is 10, and the bottom one is 11.6 repeating. And keep in mind, this bottom current, that is the short circuit current, right? The current flowing through this bottom loop, bottom mesh, excuse me, is the short circuit current that I'm looking for. So I claim that you should be able to get the Thevenin resistance, that is the resistance of this top portion, by taking the ratio of the Thevenin potential divided by the short circuit current. Well, let's check it. 8.75 divided by 11.6 repeating. Okay. And of course, 11.6, that's 35 thirds, right? And lo and behold, I guess this shouldn't be a surprise. We have 35 fourths. There we go. Shameful. 35 fourths divided by 35 thirds. And so we get 3/4 of an ohm. Cool. So it works either way. In fact, whichever way is easier for you to calculate, go that way. Okay. Sweet. Good, 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 good. Try another one. Let's go at it. Find for the load resistor. So we'll try this one right here. So 2 is the load resistor. For the load resistor, find the Thevenin voltage and the Thevenin resistance for this circuit. Go ahead. Take a minute. Go at it. You got it? Good, 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 good. Okay. So we're rocking and rolling here. So first off, let's go ahead and remove the load. So we're going to get rid of this guy right there. And then we have to calculate what the potential drop is across these two open terminals, which I have somewhat covered up now. We need to find the potential drop across those two terminals. Okay. Yeah, let's go ahead then. Since I have a bunch of current supplies on the exterior of the loop, let's go ahead and do mesh current. And so I will call this mesh number 1. There's 1. This one's mesh number 2. 2. And I guess this one's going to be mesh number 3. 3. Okay. So let's go ahead and apply mesh current in order to get the current. And once I know current 3, okay. Once I know the currents, I can find the potential difference. So let's go at it. Let's look at current 1. Well, mesh current 1 better be equal to 2 amps. And again, that's due to this independent supply. Mesh current 2 is going to be 3 amps. And we've got this 3 here. Okay, well, what do we have? We have minus I3 times 6. So let me put the 6 out in front. We have minus 6 I3. And then because we don't have a connection here, we have minus 3 I3. Okay. And then we have plus 30. And that whole rigmarole better be equal to 0. Right? Cool. Well, we've already got the top 2 answers. I guess we better find this bottom one. We get I3 is equal to 30 over 9, or if you prefer, 10/3 of an amp. Not so bad. So what do we have here? Let's see. Well, we're gonna, because of the direction I chose right here, we are going to have to go up, and then we go up again, then we go down, and then we go up, and then we have our difference, right? Okay, so if I want VTH, okay, I'm gonna have a jump here, so a jump of 4I1. I keep traveling along. I'm going to have a jump of 4I2. Keep traveling along. I'm going to get a drop of 30 volts. And then I'm going to get a jump of 3I3. So what's that going to be equal to? Well, I2, okay, I1, so this is 8 plus 12 minus 30 plus 3 times 10/3 equals 20. We got 20, we've got another 10. So I've got 30 minus 30, so I get 0. VTH equals 0. Which means the short circuit is also going to be 0. Okay. Life matches with what we had previously. That's always good to know. Okay. I forgot about that. So we see that, using the short circuit technique here isn't going to help us find the Thevenin resistance. Okay, well, let's go ahead and use that technique where we deactivate the sources. Might as well. This is just practice anyway. So let's go ahead and deactivate the sources. And what that means is that anywhere that we see a current supply, we're going to pretend that that's a break. So we break those two as if those don't exist at all. And anywhere where we see a potential supply, we are now going to make that a wire. So to redraw from the perspective of the terminals, we have a 3 ohm and a 6 ohm resistor, 6 ohm. And of course, if you want to, you can always redraw this. Then we have to go through a 4 ohm and then another 4 ohm. And then we're back at the bottom terminal. Okay, well, that means that we have to calculate this 3 is parallel to 6. And then we're going to have to add in that 8 ohm resistor. Okay, so call this one equivalent or Thevenin. Those, for this situation, those are interchangeable. We have 1/3 plus 1/6. So the -1, and then I'll put a +8 in there. Okay. Well, let's see, 1/3, 20 plus, okay, yeah, that's right. 1/3 plus 1/6 gives us 1/2, and that's inverted. So we have the inverse of 1/2 plus 8. And so here we get that the Thevenin resistance is a 10 ohms. So there we go. Of course, granted, the Thevenin supply is 0, so that's kind of boring. But at least this is practice. Cool, huh? Yeah, good. Okay. Should you try one more? Let's try one more. Here, we've already done this one again, but let's go ahead. Let us assume that the 1.5 ohm resistor is our load. Let's go ahead and find the Thevenin potential and the Thevenin resistance. Got it? Yeah, good. Just to change it up, yeah, let's go ahead. Let's find the Thevenin resistance first. And I'll do it by deactivating the sources. And that's just me again. And so what do we have here? We have our open terminal. We have a 5-volt supply and a 7-volt supply in parallel. Right? Oh, 7 volt just comes straight down. There we go. 7 volt. Or 7 ohm, excuse me. 17 ohm. That 1 amp supply is ixnayed, removed from the circuit, as is the 2. And so we have a 6 ohm resistor that we can travel through, another 6 ohm resistor, and then we arrive back at the final terminal. And now we can see, well, we have this branch, this left branch is 17. And so we have two 17 ohm resistors in parallel. And this is the advantage to having done that source transformation first, is that this should look familiar as we came up with that earlier. Okay. And then so we get that the Thevenin resistance in this situation is 17/2 ohms. Remember, two resistors of the same value in parallel, the equivalent resistance is if you cut it in half. Now, we could have gotten that doing the short circuit as well. So now what we have to do is we need to evaluate the circuit with that load resistor removed, the short circuit. Well, harumph, what's probably the easiest way? I guess I'm going to do mesh current again. And again, it's because I have a lot of exterior branches, and it helps that those exterior branches also have current supplies. 3. So we already see that my mesh current 1 has to be 2 amps. My mesh current 2 has to be 1 amp. And my mesh current 3, it looks like, okay, going clockwise, I have negative 6, I3 minus 1, minus 6 I3, minus 5 I3, minus 2. Oh, excuse me. I've got my mesh currents mixed up here. Excuse me. I1 is 2, and I2 is 1. Oh, good gravy. Why did I decide to do it that way? I don't know. And then we have minus 17, I3. And then last but not least, a jump of 34. So I'll put a jump of 34 here. Let's put 34 here. Okay. And that whole rigmarole equals 0. Sorry, I ran out of space. Okay. So we'll double check this again. We have a I3 minus 2 amps, negative 6 I3. We have a negative 5 I3 minus 1 amp, a negative 17, and a plus 34. Okay, we got everything here. And so we have an expression that allows us to find the value of I3. I'll go ahead and move the 34 to the other side. So I have minus 34 equals, no matrix stuff even needed. So I've got minus 6, 12, 17, 34. So I have a negative 34 I3. And then in addition to that, I've got a positive 12 plus 5. So I have a plus 17 there, right? The 6 times 2, the 5 times negative 1. Well, okay. So we can see that we have something like negative 51 over negative 34. So I3 must be 3 halves. Cool. Well, I guess the easiest way to get the potential difference now would be to consider this branch. And so we get that the open circuit potential, or the Thevenin potential if you prefer, is going to be, well, let's see here. We'll get a drop of 17 ohms times 3 halves. It's a drop, and then we get a jump of 34 volts. So we get 51 over 2 plus 68 over 2. Or at the end of the day, 17 over 2 VTH. Hey, what does that tell us about the short circuit current? Yeah, you could see the short circuit current's going to be 1 amp, right? Look at the Thevenin resistance, the Thevenin potential. That gives you an idea about what the short circuit's going to be. Okay. Cool. And again, we're home free now, right? Now we can model this whole rigmarole as, oh, let's get the downside right. Okay. We can model this whole rigmarole as the Thevenin potential, 17 halves, with a Thevenin resistance of 17 halves omega. And then we hook in our load resistor, which was 3 halves, 1.5. And again, we can find the current through that. Why not? We'll go ahead and find the current through the load just for completeness. So the current through the load is going to be 17 halves divided by 20 halves, which again, 17 over 20. So this is 100 minus 15. So this is 0.85 amps. There you go. And notice that it's flowing counterclockwise. So you could probably put a negative sign in there too. Cool, huh? Okay. Well, I'll call it quits there. I think maybe I'll get another video posted with some more example problems. But that's it. We are done with chapter 3. And hopefully you see now why I kind of put that idea of source transformation in with the Thevenin resistance, or Thevenin equivalence in the Norton circuits. It's because those are essentially the same ideas that you're applying. So I think that's all we have for today. Thank you for your attention. I'll see you next time.